It's the last one of the day. Okay, so here's a second spring example for a spring force, and it actually is going to include a lot of different stuff here. So what we have in this problem is a 5 kilogram or 49 Newton block, and this is nice because someone was kind enough to give you both the mass and the weight of the block. So this is the weight right here. And it's pulled along a horizontal table by a horizontal spring. So here, let's draw ourselves a little table because we don't have a picture in this one. So we got to use our imagination. So it's pulled along a table by a horizontal spring, and the table has a coefficient of friction between the block and the table. So there's some friction under here. I like to draw my friction as like squiggles up and down, just what I've always done. And we know that coefficient of friction, that value mu is equal to 0.31. And remember, that's like newtons per newton, so it's kind of unitless. So it's being pulled along by a spring here. And we know when the spring is stretched 4 centimeters, which is 0.04 meters. So that's going to be important because that value right there, that is like a displacement. That's our x value. The block accelerates at 2.2 meters per second squared. So this here is our acceleration. What we need to do is we need to calculate the spring constant of the spring. So we're actually looking for in this problem for K. We're looking for the strength of the spring here. So we've got a little bit of everything going. So let's try to figure this one out. Combine all of our F equals ma knowledge with springs and friction to, get ourselves an answer. So the first thing we should do is, while we do have a nice picture here, let's actually draw this as a free body diagram. If we draw it as a FBD, we have our block here, and our block is being pulled, let's say, to the right by a spring force. We know a spring force is equal to kx, and technically it's like a negative kx, but that negative only represents the direction of pull opposite of the extension or compression. Really, we can just use our free body diagram to show the direction of this, and it's pulling to the right here, so nothing too crazy to think about. And we also know that there's some friction acting to the left here. We know friction is fun, so we can say friction, or this F, equals mu times n, the normal force. And because we do need to think about this normal force a little bit, it's also important for us then to think about the fact that there is a weight pulling down on this block, which was actually given to us as 49 newtons. And that weight is equivalent to the normal force in this problem because we are on a flat surface. So the normal force is equal to 49 newtons as well, and that's going to be helpful because it's going to slot into there. If we want to set up our classic Newton's second law, F equals ma, then we first need to figure out what direction is positive or negative. And specifically, we're talking about this block sliding to the right here. This is the direction it's accelerating. So we know we're only truly caring about these two forces here. Our vertical forces aren't really interesting in this problem. They're equal and opposite. Our box isn't like accelerating into the air, falling through the table. So we really just need to worry about, for left and right, what do we like to be positive, what do we like to be negative. I always recommend that the direction of the acceleration be positive. So I'm going to say here, let's just make the right direction positive, and that'll make our 2.2 for the acceleration a positive number. Let's just make the left a negative number. Okay, let's just try that out, see where it goes. If you want, you could have flip-flopped that, but then your acceleration may be negative. Well, it will be negative if you flip-flopped it, and that's just one more thing to keep track of. So I like doing it like this. If we set up our equation then, we need to add our forces, and we have two of them, one to the right, one to the left. Those are the ones we care about. So let's put in the spring force. It's positive because it's going to the right, and we call it right positive. And then we add the negative friction, so minus friction, and this equals ma. And you may have noticed that, hey, why didn't I just put kx minus mu n? Well, I could have, but I really like to designate like what I'm thinking about in the problem, my spring forces, my friction forces, and then I like to go back and put in what I'm actually dealing with. So if we now go back and plug in some numbers here, or put in some like equations, well, I know the spring force is going to be kx minus mu n equals ma. So that gives me a better idea of where everything came from. And if I actually have my numbers now, well, I can say that k, and this is what we're looking for, multiplied by x, which up in the problem was given to us as 0.04 meters, and we want this to be in meters. That's our SI unit here. So 0.04 meters, minus our coefficient of friction, which was 0.31, multiplied by the normal force, which is technically equal to the weight here, which was mg, but they gave it to us as 49. So we actually know the normal force just right there. This will equal the mass, and in this problem they give us the mass just in the beginning of 5 kilograms. Very, very kind. So we can just say 5 kilograms multiplied by the acceleration, which is going to the right, the positive direction, of 2.2 meters per second squared. Okay, so that is our entire setup on this problem. We just drew a free body diagram, listed our two forces that we needed, checking for positive and negative directions, writing everything out in a little bit more detail, and then plug in numbers. And if we look at this, there's only one thing we don't know, the spring constant, the strength of the spring, but we only have one equation and one thing we don't know, so we can easily solve this. We just need to do a little bit of algebra and put some stuff together. So if we start that algebra out, let's multiply some of these terms together. 5 times 2.2, that should give us 11 newtons right here. And then on our left side of the equation, 0.31 times 49, I don't know what that is. 0.31 times 49 is 15.19. So there's a minus here, minus 15.19. And these are all in newtons because they're all going to be forces. And then we're going to have our 0.04 meters again because that just brought down. And then our spring force, or our spring constant. I can now add the negative 15.19 over to the other side. When I do this, I'm going to have k times 0.04 equals, let's see, 15.19 plus 11. That should be 26.19 newtons here. And then I just need to simply divide by 0.04 meters. Whooshing! Divide by 0.04 meters. My units are newtons per meter, which is exactly what I want for a spring constant. And when we do this division, we find that our spring constant k equals, whoops, that's not division. It's important to divide and not subtract. We get a value here of 654.75 newtons per meter. And that's our spring constant there, okay? Spring constants can be very, very small numbers. They could be like 1 or 2. You need small spring constants for things like a pen, but they could be very, very large numbers as well. If you need springs for a bumper car system or shocks on a car or a pogo stick. So pretty much anything above 0 will work for a spring. If your spring constant is 0, that means your spring doesn't exist. And if you get a negative number for your spring constant, that means you've broken some math. So if you're ever doing some higher level differential equation problems with spring constants and you get a positive or negative answer, it's only the positive one because they have to physically exist. Okay, so that is how we can use an F equals ma with not only a spring and looking at it, but also with some friction as well. So it was a kind of like full problem there, a lot of stuff going on, but in the end, just an F equals ma problem. List your forces, put your directions down, and then work out the math, and then you're finished. Take it easy.